However, there are some more complicated problems where you have a positive charge next to a sphere. Somehow this thing does not appear like a sphere to me on my computer screen, but it's supposed to be a sphere. Okay, so if you put the positive charge here and a negative charge here, and if you adjust its location, the location of this negative charge properly, okay, the picture is not very well drawn, but it should be something that is actually symmetric. Okay? If you put this positive charge and the negative charge at the correct location, then you can actually work out a solution where n cross E equal to 0. Okay, I'm not going to work out the details for this problem, but it has been worked out in Ramo et al. Okay, I can even give you the page number, but the page number is given in the lecture notes. You can go through the mathematics and find the location of the negative charge such that the two charges together, the positive charge and the negative charge, would produce electric field that cancel each other on the surface of the sphere. And you can also repeat this for a cylinder. Okay, just a lot of mathematics. Okay, but it turns out that this problem is also solvable. That is, if you have a dielectric interface, a positive charge over there and a negative charge over there, and if you pick the strength of this image charge to be given by this thing over here, you can show that the boundary condition is satisfied on this surface. What is the boundary condition that we should have on this surface? It's not the PEC now. Okay, what do you think are the boundary conditions there? It's an electrostatic problem. So what are the two boundary conditions that we should have on that surface? Okay, anybody wants to suggest the kind of boundary conditions we should have at that surface? So if it is an electrostatic problem, we only need to solve two equations. Okay, the two equations that we need to solve are divergence of D equal to rho, and since there's no charge except for plus charge over there, okay, so we don't have to worry about rho except for this point over here. The other equation that we need to solve is Faraday's law, but since this is static, Faraday's law just become that. Okay, so now if you eyeball these two equations, what are the boundary conditions that follow from these two equations if you have to solve them? What is, maybe you go with the simple one. If you have Faraday's law for this problem over here, what is the boundary condition that you should have? Anybody? Well, we learn how to eyeball a PDE and actually very quickly determine what the boundary condition should be. Would anybody like to tell me what the boundary condition should be if I just eyeball Faraday's law and ask myself what the boundary condition should be at this interface? Let me see. If you're not going to answer, I'm going to call your name. Okay. What about Jason? What do you think is the boundary condition I should have for this Faraday's law?
Is it the tangential electric fields are equal?
Yes, tangential electric field continuous. Very good. N cross E continuous. So you have N cross E continuous at that surface. Okay, you should have this continuous. There's one boundary condition. What is the other boundary condition? We would have to solve Laplace's equation, because if you were to solve this equation, then E is equal to minus grad phi, and then D is equal to epsilon E would be epsilon grad phi. And then from this equation, you will have divergence of D would be minus divergence of epsilon grad phi equal to rho. Okay, so those are the two equations that we need to solve. And actually, the second equation looks almost like Poisson's equation, except that it is more complicated than that. Okay. However, if you assume that epsilon is a constant in this region and epsilon is a constant in that region, then the Poisson's equation actually becomes like quite simple. Divergence of gradient of phi is minus rho over epsilon naught in this region, and divergence of gradient of phi equal to minus rho over epsilon 1 in this region. Then you solve these two equations, and then those two equations actually follow from these two equations. Okay, they follow from these two equations, and they're second order PDEs. So they need two boundary conditions. So the two boundary conditions that you have told me are tangential E is equal to continuous. The other boundary condition is that the normal flux, or actually I haven't asked you about the other boundary condition. The other boundary condition that follows from this this thing, okay, that if I were to go from here to here, the boundary condition that it induces is D1, D2 is equal to surface charge. But there's no surface charge in this problem. Rho of S is equal to 0 at this surface. So we can set this to be 0. And then the other boundary condition will be epsilon 1 E1 minus epsilon 2 E2 equal to 0. And actually, we just have epsilon naught and epsilon 1. So it will be epsilon naught E naught minus epsilon 1 E1 equal to 0. So those are the two boundary conditions that we need to solve this problem. And then if you solve it, and it's quite difficult to do, but it can be solvable using image theorem. And you can actually put the image to have this strength, and it will produce electric field in the whole of space. And then you can put a source at this point, it will produce an electric field that is in the whole of space. You can add the two solutions together, and you will find that both of them together will satisfy this boundary condition. The other boundary condition is tangential E is equal to continuous. Okay, tangential E is continuous, and that is the same as phi continuous. Okay, phi is continuous. You can actually show that the phi being continuous will ensure that n cross E is continuous, because E is equal to the gradient of phi, and if phi is continuous from this surface to that surface, it will ensure that tangential E is also continuous at that surface. Okay,